So I need to discuss one more topic before we can wind up today. Okay, the last thing I want to discuss is I want to now remove one more constraint. Clock edges are not instantaneous. Okay, in that case, I want to see how to analyze setup, hold, clock to queue, whatever it is. Okay, so my clock edges are going to look like this. And my data, let's say this is a positive flop, positive edge flop. Data is now going to change like this. D1 to D2, and any further change should get ignored until the next D3, D4. Q basically should just, right? I do not know what this state is, right? And from the clock edge, this change should happen. Okay, so this will be D2, and after the thing it will become D4. Okay, so you cannot analyze this in a theoretical way like we did for earlier examples. You have to go to simulations. Okay, so I want to now tell you how you can figure out what the setup and hold time of your flop is through simulations, right? So first we will look at what is the setup time. Okay, I want to see what is setup time. Actually, you look at both of these together, setup and clock to queue delay. You will look at it together. Okay, so what we'll do is I'm going to, this delay is TCD, clock to data, data to, yeah, TDC, sorry, data to clock delay. Okay, and what is this delay? TCQ, right? Then there is another delay which is basically the time from data to queue, TDQ. Okay, so what is TDQ equal to? TDC plus CQ. So now my point is I want to make TDC smaller and smaller. That is, I'm going to bring the data change closer and closer to the sampling edge and see when the flop fails. So the thing is, the flop failing is actually more an extreme condition that may, it may tolerate more delay. The point is, as I bring the data edge closer and closer to the clock, that feedback loop will start entering metastability region. Okay, so if I have, look at this thing. Just for simplicity, I'll draw this without any, without cutting out the feedback, right? Overpowering the feedback. So what is happening is, my data change is happening, my clock is also changing, and it so happens that clock is changing here, data is also changing here. So when the clock actually cuts off, right, when the clock cuts off, remember that this is my sampling edge. So when it samples, right, and the clock goes from 0 to 1, my L1 is going to go to what state? Opaque. L1 will go to opaque state. That means it's going to just hold the data in the feedback mode. Okay, now let's assume that D changed something like this. Okay, almost in sync with the clock. At somewhere here, the clock will cut off this tri-state inverter path, right? And it is very much possible that this capacitor here will charge not all the way to VDD or ground or discharge all the way to ground. It may come and land up somewhere near VM, right? And I already told you that that is also a reasonably, it's a metastable state. If this comes to VM, this will also be VM, and it can remain in that state for a long time until noise or something comes and switches it one way or the other. Okay, so what you see is, if this happens, the QM, right? Let's assume there's no polarity changing. QM will actually charge to VM like this for some time and then go high. You can do this in your simulation and check. Bring it closer and see what happens to QM. QM will go to this metastable state for some time, and the closer and closer you bring the data change to the clock, this time will keep on increasing. It will remain in that thing, and ultimately, because of some capacitive coupling or something, this QM will switch to the actual value. Okay, so in this example, D and QM are the same polarity. If I keep bringing this edge closer and closer, at some point this will go to the wrong value also. It can switch to the wrong value. QM can switch. So this is completely wrong, right? This is correct, but it will happen with some delay. That means even though the setup time was correct, data could be sampled correctly by the flop, the clock to Q delay will go up significantly, because only if QM settles to the correct value will Q then reflect the right value out, right? That is what we are going to now exploit in order to give a very formal definition to setup and hold time. Okay, so what I'm going to do is I'm going to now plot So I'm going to bring my clock edge closer and closer, right? So I'm going to plot versus TDC. Okay. And what are the things that I'm going to plot? I'm going to plot TCQ and TDQ. Okay. I'm going to plot two things. TDQ, TCQ. Okay, and remember that TDQ is nothing but TCQ plus, or rather TDC plus TCQ. Okay, so let's assume that TDC was a very large value. That means the data change, okay, the data change has happened far away from the clock edge. What should be the value of TCQ in that case? Will it be minimum or maximum? Yeah, it will be minimum, because the data change has settled correctly. There is no metastability problem. The feedback loop would have settled, and the output also will appear very quickly. Therefore, if you look at my TCQ for large TDC, it will be some minimum value. Okay, TDC, right? As I bring the TDC closer and this is TCQ. As I bring TCQ closer and closer, TDC closer and closer, what will happen to TCQ? It will start increasing, right? The clock delay will start increasing like this. And at some point it can go up significantly, because the metastability time will be very large after that. Okay, you have to simulate this to see it. How will the plot of TDQ look like now versus TDC? For large value of TDC, what is the equation like? Is it a constant? It's a straight line because it's TDC plus TCQ, and TCQ is a fixed number now, right? Therefore, it's going to be a thing like this. Correct? So as I bring my TDC, right, my data change closer and closer to the clock edge, my TDQ actually is coming down. Why is it coming down? Because TDC itself is reducing. TCQ is a constant number. TDC is reducing. Therefore, the delay keeps reducing as I bring it closer and closer to the edge. But at some point, because TCQ is now going to go up, TDQ also starts going up. Right? And therefore, you will see that this takes a turn like this and goes up. Of course, remember, for any value of TDC, TDQ should be greater than TCQ. So it will always be above that thing. Okay, this is my TDQ. So what you do is you pick this time when it is minimum. Okay, let me redraw this slightly so that I can make it more exaggerated. Okay, you pick the time when TDQ is minimum. You get a particular value of TCQ, right? That TDC for which TDQ is minimum is defined as the setup time. Setup time is formally defined as the time when data to queue change, data to queue delay is minimum. That TDC when this delay is minimum. Now you get two different TCQs right here. If TDC were large, then the TCQ is very small. But if TDC were at setup time, then you see a larger TCQ. This is the origin of contamination and propagation delay for clock to queue. So this I will call as TCCQ, right? This point. And this point I will call as TPCQ. Okay? So when you make a flop, you have to do this exercise. Take TDC closer and closer. And now again you have to do it for both 1 and 0 transition. It will be different delays. Okay, you have to, because the PMOS and NMOS are not identical in reality. So you have to do it for both transitions. Plot your TDQ and TCQ versus TDC. See where my TDQ becomes minimum. That point is defined as your setup time. Right? That's TCQ, right, is defined as the propagation clock to queue delay. And when TDC is far enough, that delay is called the contamination clock to queue delay. So remember, like I told you, the origin of contamination and propagation delay are very different for flops and combination circuits. And this is the origin for sequential circuits. Okay.